Okay, 5.2, solve linear systems by substitution. Substitution is an algebraic method of solving a system of linear equations. A system of linear equations can be solved algebraically using the substitution method. Okay, and the point of intersection, which we've just found using graphing, is the point at which the cost to produce an item is equal to its selling price. And this is going to be for the word problems that we're going to focus on. Okay, so here are the steps for the substitution method. First, we want to isolate one of the variables. Okay, the easiest way to do that in the note here is that if the variable has a coefficient of 1, then what we're going to do is we're going to substitute that expression from this equation into the other equation. Okay, and then we're going to solve for the only variable that should be in there. Then we're going to substitute that answer, that answer to that variable, back into one of the original equations to find the value of the other variable, right? Because there's always going to be two variables. And then we're going to write the solution. I think in Word it's a little bit more difficult, but hands-on, we'll see that it's not bad. Okay, example 1, use the substitution method to solve for the following linear systems. So we have y equals 3x minus 13, and then y minus 2x equals 1. So here's the thing. This y is already isolated. It's already y equals. So what we're going to do is we're going to take this expression and we're going to substitute it into the other equation where the y is. So we're going to get 3x minus 13, bring down the negative, bring down the 2x, equals 1. Bring that all down. And now all we have to do is solve. So bring that negative 13 to the other side. It becomes positive 13. So we have 3x minus 2x equals 1 plus 13. Okay, we get x equals 14 and we're done. So that's going to be our x value in our point of intersection. Now, we have to take that x equals 14 and we can plug it back into either of the two original equations. But here's the thing. Y equals 3x minus 13 is already isolated for this y value. So if we sub this back in, we don't have to rearrange. So y equals 14 minus 13. Okay, you get 42 minus 13, which is 29. So y equals 29. Okay, and then our point of intersection is 14, 29. Okay, B, 4x minus 7y equals 20, x equals 3y plus 10. Well, x is already isolated, so let's take this 3y plus 10 and let's sub it into where the x is. So copy out that first equation. 3y plus 10 minus 7y equals 20. What we're going to do is we're going to expand that 4 into the bracket. We get 12y plus 40 minus 7y equals 20. Okay, bring that 40 over, so minus 40. The 12y minus 7y, we get 5y. And then 20 minus 40, I get negative 20. I'm going to divide out by 5. I get y equals negative 4. Okay, so in the point of intersection, the y is going to be negative 4. Now we have to find the x. The x is already isolated, so let's use that equation. X equals 3y, which is negative 4, plus 10. So negative 12 plus 10, which is negative 2. Okay, sub that into here. So our point of intersection is negative 2, negative 4. Okay, C, we have x minus y equals 5, and then 3x equals 5y plus 9. So here's the issue. Nothing is isolated here. However, the coefficient of both x and y Well, x is 1 and then y is -1. So let's actually just, let's erase that and let's isolate just for the x. So if we had x minus y equals 5, we're going to bring that negative y over. It becomes positive y, and we get x equals 5 plus y. Now we're going to take that and we're going to substitute it into the second equation. So let's rewrite this second equation. 3 bracket 5 plus y equals 5y plus 9. Distribute that 3 into the bracket, we get 15 plus 3y equals 5y plus 9. Let's take that 3y over to the other side. It becomes negative 3y. Okay, and let's bring this 9 over to this side. It becomes negative 9. So the constants are on the left side, which is 15 minus 9, and the y values are on the right-hand side, which is 5y minus 3y. So we get 6 equals 3y, divide out 3, y equals 2. Sorry, this is 2y. 5y minus 3y is 2y. My mistake. Okay, so y equals 3. So in the point of intersection, the y is going to equal 3. Now we have x equals 5 plus y, which is our rearranged formula. We already did the legwork of rearranging it, so let's just use that one. So 5 plus 3, which is 8. Okay, so we put this in, and our point of intersection is 8, 3. Okay, example 2, Rachel's an economist. She evaluates the effect of changing the price on the supply and the demand for a product. The selling price in dollars, so Y, of a product is related to the number of units sold, X, according to these two equations here. So this question wants us to solve this system algebraically. Okay, so we've been using substitution, so that's what we're going to do. And then we're going to talk about what the solution represents. So we have y equals negative 0.4x plus 10, and then y equals 0.6x plus 2. So in this question, we have two variables that are actually isolated. So let's just take this expression here, and let's substitute it in here for y. So we actually are going to equate these two. Negative 0.4x plus 10 equals 0.6x plus 2. Okay, let's take this negative 0.4x, bring it on this side. It becomes positive 0.4x. Let's take this 2 and bring it on this side. It becomes negative 2. So we get 10 minus 2 equals 0.6x plus 0.4x. So we get 8 equals x. Now, both of these are already isolated. I'm going to go ahead and choose the one that has positive values, just to be a little bit lazy. And I'm going to go ahead and substitute that 8 in. So I get 4.8 plus 2. I get y equals 6.8. Okay, so our point of intersection is 8, 6.8. Okay, and what this means is, okay, the selling price of dollars is y, number of units sold is x. So therefore, 8 units are sold at a price of 6.8, so $6.80, to break even. And that's what it's called.